Hello, my name is Kayra Kılıç, and in this video I will present my Physics 101 lab project. In my experiment, I aim to demonstrate the effect of equal constant acceleration on relative velocity. To achieve this, I designed my experiment in 4 parts. For parts A and B, pucks were launched with similar and different velocities respectively. For parts C and D, pucks were released with a sign inclination of 0.14 and 0.16. In this video, I will be explaining my experiment theory, equipment, processes, findings, and conclusions. To begin with, I would like to state our relative velocity formula. In this experiment, motion of the pucks were aimed and assumed to be on one axis. Hence, relative velocity of puck 1 with respect to puck 2 is found by subtracting the velocity formula for puck 2 from puck 1. In my experiment, we focus on the below equation. When accelerations are equal, relative velocity remains constant, and it is equal to the difference between the initial velocity difference. Instantaneous velocities are calculated using the Lagrange formula. These instantaneous velocities are used to calculate relative velocities at specific time points. Accelerations on the inclined plane are calculated using this formula involving theta and constant g. Percent error and variance were calculated. In some of the cases where our theoretical value is equal to 0, percent error method failed to give us a result. Hence, we calculated variance according to our theoretical value in these cases. Now, let me explain the process. For the experiment, I used a frictionless air table with 2 pucks, 3 rulers, tape, carbon paper, regular paper, and an incline block. Firstly, I prepared my experiment setup. I placed my paper, attached my 2 rulers. Then I set the spark timer frequency to 50 milliseconds to both obtain enough data points and to get meaningful readings with my measuring devices. Then I started the experiment by performing the first and second parts of my experiment. For part A, using another ruler, I launched the pucks with similar velocities on the flat plane, pressing the frictionless and spark pedals. For part B, I launched the pucks with different velocities, pressing the frictionless and spark pedals. For part C and D, I used an incline block which had angles with sign values corresponding to 0.14 and 0.16 respectively. I released the pucks, pressing the spark and frictionless pedals, obtaining my data points. I repeated this step for both parts C and D. Then I recorded displacement values I obtained from all parts I stated. After doing calculations, I obtained tables. Using these tables, I plotted the following graphs. This graph of part A of displacement with respect to time, with small y-intercept value shows that experiment was well performed. However, this part of the experiment aimed to launch pucks with equal velocities, and examining the slopes from the formula, there is a small difference in velocities of pucks. This can be attributed to human error, such as applying different forces in the beginning. This graph of part A shows that the velocities that pucks are launched with are similar, and the slopes of the lines which are close to 0 mean that there wasn't a major external effect on the pucks. This graph of relative velocity with respect to time shows that under equal acceleration of almost 0, pucks launched with the same velocity yields relative velocity near 0. Variance is calculated in this case because the formula for percent error fails where theoretical value is 0. The variance is low in this part, further proving experiment was performed properly. This graph of part B of displacement with respect to time with small y-intercept shows that part B was performed properly as well. This graph of instantaneous velocity with respect to time shows that the accelerations and the outer effects are negligible when we look at the slope of the values of the lines. The graph of relative velocity when we check the slope near 0 means that relative velocity remains constant like in part A. The small variance we can see here again means that this part of the experiment was performed well. Examining the inclined surfaces of part C and D, we can see from displacement graphs that values of two parts followed similar patterns. On the other hand, examining these instantaneous velocity with respect to time graphs and checking the slopes, we obtain the accelerations. It was expected that this graph had an acceleration of 1.372 here and 1.568 here. However, the experimental results are different. This could be caused by human error of not using a ruler when releasing the pucks, or neglected air and surface frictions. Checking the parts C and D, relative velocities are near zero despite the error in acceleration. This is because, even though the accelerations aren't exactly as expected, they are very strongly similar. The small variance supports the reliability of these parts of the experiment. These graphs of relative acceleration with respect to time demonstrate that under similar acceleration, relative velocity remains constant and in these cases equal to zero. Increasing or decreasing acceleration does not affect relative velocity given that both are experiencing the same acceleration. In conclusion, this experiment successfully demonstrated the effect of equal constant acceleration of two objects through four different parts, two of which had constant accelerations, while other two had acceleration near zero with similar and different velocities. The experiment concludes that the theory was successfully observed using the stated lab equipment and processes. The errors in this experiment are minor and could be avoided by further minimizing human involvement in the processes, by using electronic launchers, or by better isolating the system where air friction is smaller. Thank you for listening.